Welcome to this training on Bluetooth ESL and PAwR. In this training, we will see how to use periodic advertising with responses in one-to-many applications. We will go into the details on Bluetooth ESL and how the standard works. Finally, we will learn how to get started developing with PAwR and Bluetooth ESL. Let's start from the agenda. First, we will introduce the requirements for one-to-many use case, and we will understand why a new release of Bluetooth was needed to address this use case. Then, we will explain what PAwR brings to the one-to-many use case and what the new features are in Bluetooth 5.4. Then we will go into details of Bluetooth electronic shelf label, service and profile, with both theory and the real demo. We will see PAwR in action with another demo where we will have more than 50 low-power devices interacting with one access point. Following that, we will cover the Nordic offering for Bluetooth low energy, including periodic advertising with response and Bluetooth ESL. And finally, we will see how to learn more about this application and how to get started quickly, showing an out-of-the-box demo and the Bluetooth ESL tutorial. Let's start now with the one-to-many use case, understanding the requirements first. We want to address a simple question: how can we handle many low-power devices with a single access point? Let's say that we have a star topology and we assume devices are within range. We want the devices to be low power. So they will need to be sleeping most of the time, but at the same time, they need to be able to receive messages from the access point and send responses. Basically, we want some bidirectional communication with relatively low latency. Since we have many devices, we need a system with low interference. To achieve this, we need also all the nodes to be somehow synchronized to the access point. There must be a synchronization mechanism so that the tags, the devices, need to know when to wake up, when to send data, and when to go to sleep. In the following few slides, we will see that before Bluetooth 5.4, it was not possible to meet these requirements with the Bluetooth low energy. This is a good exercise for two reasons. First, we will better understand why PAwR was needed to be introduced to address this use case. And second, we will naturally understand why this new feature is building on top of the periodic advertising concept available in previous releases. As mentioned, now we want to see how, prior to the Bluetooth 5.4, this use case could have been solved, and we will analyze pros and cons of each solution. Let's say that we are using Bluetooth 5.3, for example, and so how can we address the one-to use case using that release? Here, a first possible solution. In this case, all the tags are advertising randomly. The access point, the central, can constantly scan for tags, and only when needed, it can connect to a specific tag over Bluetooth low energy. So the connection happens on a case-by-cases. With the Nordic soft device controller in an RF Connect SDK, it will be possible to connect concurrently up to 20 devices and exchange data. Even if this approach is simple, it presents some disadvantages that make it not so scalable. The noise level can be significant because all the tags will be advertising at the same time. If you have 50 or 100 devices already, you may have a lot of collisions which slow down the system. The tags are also not synchronized to the access point. They are not aware of what's going on in the access point and vice versa. The access point does not know what's going on in the tags unless the access point connects to each tag. Power consumptions presents some trade-offs which are not good for this use case. If the tags advertise fast, it will not be low power. If too slow, it will increase the latency of the system. And it takes even longer to connect to a tag. Finally, as mentioned before, there is a limited number of concurrent links you can support from a single access point. So you cannot easily and fast enough send commands and collect data from all these tags. Again, let's see a different way to address this use case with previous releases. In this case, it's possible to have tags to be scanners and to have access point to be an advertiser. This has a big advantage compared to previous scenario. The tags are quiet, they are not advertising, so reducing the overall noise. When the access point wants to connect to a tag, the access point needs to advertise and include in its advertising packet the address of the tag to which it wants to connect to. The right tag receiving this message can then wake up and request a connection. However, this implementation has also several challenges. Scanning is not low power, so the tags will not be low power. They do not know, indeed, when to expect the next message from the gateway, because there is not a synchronization in place. So they need to scan almost all the time. But if you scan for longer windows, you will increase the power consumption. Another challenge is that the gateway is not aware of the status of the tags. Basically, the gateway is not in control of the system. These are the challenges that make this implementation not really suitable for this use case. Prior to Bluetooth 5.4, there was another alternative approach, which is worth to look at because it is a step forward from the previous one and a step closer to the solution. In the previous slide, we liked the idea that the tags could be listening, so being low noise. So they were scanners. But the problem was that the tags didn't know when to expect a message from the access point. In this slide, we see that the periodic advertising somehow solved this problem. Periodic advertising is a kind of advertising that is periodic and is performed on the data channel and requires a synchronization mechanism. In this case, we can use the gateway as a periodic advertising advertiser and the tags as a PA scanners. That means the gateway can send a train of sync packets on the Bluetooth low energy data channels. This train of sync packets is periodic. In this example, we have a periodic advertising interval of 2 seconds. In such packet, it is possible to send and include a payload. The tags are all synchronized to the access point and know when to wake up to receive this packet. So this has somehow an advantage compared to the previous solution in the previous slide. In this case, tags are low power and we have low noise. However, it has two big problems. The tags cannot send responses back. They can only receive commands from the access point. And the other challenge is that all these tags synchronize to the same event from the access point. So somehow they are all belonging to the same group of tags. They are all listening at the exact same time. And this is not scalable. You cannot address many tags with only one group of tags, because you cannot really reduce the periodic advertising interval too much, otherwise you will increase the power consumption of the tags. The result is that the access point is not doing anything for most of the time in between these sync packets. So even if this approach is not optimal, however, it brings closer to the solution. And the solution is introduced by the Bluetooth 5.4 release. The new feature that allows us to address one-to-many use case in a proper way is the periodic advertising with response, PAwR. So what is the periodic advertising with response? How does it compare with the periodic advertising that we have seen in the previous slide? What are the advantages? Compared to the periodic advertising, the new periodic advertising with responses introduces two concepts. The first concept is that the advertiser, in this case the access point, can send multiple periodic sync packets within the same periodic advertising interval. These sync events are named sub-events, and there can be maximum 128 sub-events. Peripherals, for example tags or sensors, can subscribe to one or multiple of these sub-events. In each of these sub-events, the advertiser can send a payload or request a connection to the device listening to this sub-event. Naturally, if you just want to keep the tags synchronized, you can also send an empty packet. From a PAwR perspective, there are no limits on how many devices can subscribe and synchronize for each sub-event. However, there are other upper layers aspects that can put a limit to that, and we will see later in the slides this. The second feature introduced by PAwR is the concept of responses. After receiving a sub-event, a scanner, for example the tag, can now send a response back in a specific response slot. The interesting aspect is that there are multiple response slots available for each sub-event, up to 256 by the standard, which means more than one tag can send a response back to the access point following a sub-event. It means that the access point can address multiple tags within the same sub-events, and it is still able to receive responses from it. Note that using PAwR, an access point can now send a command and receive a response back. And all of this is done in the data channel and in a connectionless way. Let's zoom in now and see a bit more in detail what's happening within each sub-event. Let's say, for example, a number of tags have synchronized to sub-event 0. You can see these tags, they are blue on the slide. The advertiser can include now a payload within the sub-event 0 and another payload in sub-event 1. All the tags that subscribe to sub-event 0 can now wake up from sleep at the exact same time, because they know when the sub-event is supposed to happen. So they can listen to the payload that has been included in the advertising sub-event, and based on that they can either go to sleep, or if they want, they can send a response back. As you can see, there are several response slots available after each sub-event. How many of these are available is decided by the access point when the access point is initialized. Each tag can respond in a specific response slot. So, who is deciding which tag should respond when in order to avoid the collisions? This is decided by the upper layer logics. The PAwR by itself, indeed, is very simple and flexible, and hence very powerful. upper layer logics are important and necessary to decide how to use this feature depending on each use case. In this example, we see 3 tags responded and then they go back to sleep. The last blue tag has also listened to the same sub-event, hence keeping the synchronization, and goes back to sleep immediately. It will wake up to the next sub-event to which it has subscribed. If the blue tag subscribed only to sub-event 0, it will wake up every PA interval. After the sub-event interval, the access point will send another sub-event addressing other tags that previously subscribed to this second sub-event. The yellow tag wakes up, processes the payload in the synchronization packet, and if there is anything to respond to, it will send a response and go back to sleep. You can see that in between these events, the access point has some extra available time. This is quite important because the access point at any time needs to be able to scan, connect to tags, or do other procedure concurrently with the PAwR. So, how does this new feature can be used in the one-to-many use case? The new feature from Bluetooth 5.4 addresses quite well the one-to-many use case discussed earlier. In this architecture, the gateway is the periodic advertise, and the tags are the PA scanners. Different tags can be assigned to different groups. Each group is synchronized and listening to one sub-events. Tags can send responses back in response slots. In this way, the system is more scalable and the access point can use more efficiently its radio resources by addressing multiple groups of tags within the same periodic advertising interval. All of this in a connectionless way. What are the advantages of this solution compared to the previous one we have seen for the one-to-many use cases? This system is low noise and bidirectional. Low noise means that all the tags are sleeping most of the time. They know exactly when to wake up, to listen to the sub-event sync packet, and to check the payload, and they can respond back only when it's needed, in a very precise way, without collisions with other tags. The system is very scalable. You can address and handle a very high number of devices, but it can also work with very few devices. All tags are synchronized to the same access point, and they can always receive something or send something. This means that there is a mutual awareness. It's low power. The tag listens for a very short period of time. If there is a message, it will respond. If there is no message, the tags can go back to sleep immediately. At any time, the access point can also connect to any of these tags and exchange data in a faster way using ACL connection or do a device firmware update. You can have different approaches to interact with the tags, either a pull approach or a push approach. We will see that in the case of Bluetooth ESL, a polling approach is used. That means that it's the access point to send commands to the tag when needed. However, for your application, you may decide also for other logics, for example, for a push approach, but you will need to define the upper layers accordingly. What are the disadvantages of using this approach? First, There is quite a complexity on the access point. Handling thousands of tags can be demanding, and so you need to do many design choices. Besides this, there are many trade-offs to keep in mind when choosing PAwR timings and other parameters, which will have an impact on the latency and power consumption, and so the timings need to be tuned properly depending on the use case. Note that this architecture is just an example of how to use PAwR to meet the one-to-many requirements discussed previously. This architecture is conceptually important to understand the Bluetooth ESL that we will see later, but nothing prevents you to use different logics for different one-to-many use cases, depending on your requirements. Indeed, as already mentioned, the PAwR is very flexible. It sets a maximum number of sub-events and response slots, but the actual number and the timing can be decided depending on the use case. You will need to decide many aspects indeed for implementing a system. For example, how to synchronize devices, as there are two ways to synchronize them to the PAwR according to the standard. You need to decide which tag should subscribe to which sub-event. You need to find a logic on how to address tags within the same sub-event. That means that if you send multiple commands to different tags within the same sync packet, tags need to understand which command is for which tag. You also need to decide how responses should work. Can a tag send an unsolicited response on a pre-assigned slot, or needs to wait always a command from the access point? And so how this tag should decide in which response slot to respond. In many cases, all these design choices are interrelated. To dive into PAwR as a generic feature and to understand all these options available, we have created a guide on DevZone, and you will find the link listed in the Nordic Bluetooth ESL tutorial. This guide will help understanding the flexibility of this feature. It is clear that depending on each use case, many things need to be decided by the upper layer. So let's first look at possible application, and then let's explore one of them in much more details. So in which application PAwR can be used? Here, imagination is really the limit. The PAwR feature can be used in many use cases. Whenever you have a one-to-many use case, this feature may have a good fit. Of course, it fits very well for the Bluetooth ESL application, which we will see later. This has been the main driver for adoption of this new feature within Bluetooth SIG. But the PAwR can be used also for other applications such as asset tracking or warehouse management. Indeed, if you have devices that are mainly stationary but can move from time to time, you can have multiple access points, and you can use a similar approach to the electronic shelf label, as we will see later. However, when a device stops somewhere, it can associate to a new access point. While it moves and loses synchronization with an access point, it can start advertise to signal the presence to all access points. And again, when it stops, it can associate to another access point to exchange data. PAwR in general can be used for sensor networks, for building automation or office management, for example. Whenever you have low power sensors that need to be controlled, it has a good fit. It can be used for smart locks when you have many locks nearby a single access point. But it can be used also in other type of applications, like classroom response systems or restaurant paging systems. Even if you have less than 100 devices to control, PAwR may help reduce the burden on the access point, which can dedicate then the resources to other activity more efficiently. So if you have many devices to be handled, PAwR in many cases is a no-brainer. But let's dig into Bluetooth ESL. Electronic shelf label is one of the main target applications for periodic advertising with responses. Bluetooth ESL requires Bluetooth 5.4 as it leverages two new features available from this release. One is the periodic advertising with responses, which we have discussed so far. The second relevant feature is the encrypted advertising data, which allows the encryption of advertising data, including the commands and responses sent over PAwR. These two new features are used heavily in Bluetooth ESL. However, as we have discussed earlier, applications logics need to be defined to use these new features in real application. For this reason, Bluetooth has introduced the Bluetooth ESL service and profile, which standardize all upper layer logics to use PAwR and EAD for the electronic shelf labeled use case. The service and profile define the upper layer mechanism, the behavior, the functionalities of the ESL tags, and define how the tag is expected to be controlled by the access point. The goal is to have interoperable tags so you can have multiple tags from different vendors controlled by the same access point. Both the Bluetooth 5.4 and the ESL service and profile are now adopted. And it's good to note that this architecture can be a starting point for many other use cases as well. So it's very educative to learn the details in the next few slides. As mentioned earlier, we want to address the one-to-many use case. We want to have a large scale. And with Bluetooth ESL, we can achieve that. By using this standard, we can handle up to more than 32,000 tags with a single access point. In fact, we can use up to 128 sub-events in PAwR, and we will call them groups, so we can have up to 128 groups. And in each group, we can address up to 255 tags. But it's not only about price tags or electronic shelf labels. We can also support sensor devices without displays. We can have a temperature sensor or other type of sensors. Basically, you can use Bluetooth ESL to collect sensor data as well. With Bluetooth ESL, the system is fast and we can meet the latency requirements from the retail industry without compromising power consumption. Just as an example, in less than 2 seconds, you can request 1,000 different tags to change display image. Or in less than 2 seconds, we can trigger an LED to start blinking. Another cool feature is that you can plan actions in advance on the tag side. For example, you can tell a device to perform an action in 1 week or 1 month in advance. With Bluetooth ESL, we are also able to establish connections at any time with one or more specific tags, while keeping sending commands to all tags and receiving responses. A connection may be needed to transfer a new price, a new display image, for example, or to perform other actions. The Bluetooth ESL system is quite robust and secure. There is a very well-defined state machine for all the tags. Most of the times, these tags are synchronized to the access point. Encrypted messages are exchanged between access point and tags, leveraging the PAwR and EAD features from Bluetooth, minimizing noise and interference. Such implementation also enables low power operation, so depending on battery size, lifetime can be up to 5 or 10 years. Finally, Bluetooth ESL brings interoperability on the tag side, while keeping the access point quite flexible, so leaving room for innovation on the access point as well. Given all these nice features, it's good to learn how Bluetooth ESL works under the hood. In this section, we will learn important details on the Bluetooth ESL specification. Basically, we will learn the upper layers logics and how the Bluetooth ESL specification uses PAwR and EAD to handle thousands of tags. Before that, some important notes. The Nordic implementation of Bluetooth ESL service and profile abstract most of the complexity. So you don't need to implement these features in software by yourself because we did it for you. However, it is very useful to learn the logics behind it so you can better use the Bluetooth ESL to your advantage. The following slides give a detailed description of the standard. However, it's important to stress that they don't replace the specification. Links to more training material and specifications are available as part of the Nordic Bluetooth ESL tutorial in the Nordic Bluetooth ESL Getting Started Kit mentioned at the end of this training. Now, let's see how Bluetooth ESL works in a very practical way. Since the standard focuses on the tag side, we will do the same and we will start from the state machine of the ESL tag. Note that in this presentation, we have taken some images from the Bluetooth profile, Bluetooth ESL service and profile spec. And the references are added to the slide, so it's easy for you to find them in the spec. The Bluetooth ESL defines the role of access point, the central device which is running the PAwR advertiser, and defines the role of the ESL, the peripheral, which we will name it also as tag in this presentation. The ESL can have display, LED, and sensors, or a different combination of these. The ESL tag comes with a Bluetooth address and needs to support at least the ESL service. But in some cases, it shall support also other services, such as the object transfer service. For example, if the tag has a display and needs to receive the images from the access point, or the device information service. Now, in the following slides, we will see the entire state machine starting from a new ESL as defined by the service, and we will cover all the major operations and interaction with the access point. So let's say that we have taken a new ESL tag which has never been associated to any access point. So this tag is in an unassociated state, as you can see in the state machine. In this state, the tag will start the normal advertising, and among other things, it will advertise that is running an ESL service. The tag is scannable by the access point, and the access point can request a connection. Up until now, we are not using PAwR on the tag side. However, on the access point, we already have the PAwR advertiser running, And while doing that, the access point can scan and request a connection to this specific tag. The tag accepts the connection, and once that is done, it will move to the configuring state, during which the tag has a ESL connection to the access point, and they can be configured from the access point. After the pairing procedure, each slide will have bond keys stored, and following that, the access point can read and write the characteristics of the ESL tag. On the top right corner, you will see which characteristics are mandatory and which are not. Here, we focus on the most important ones. For example, the access point will transfer the absolute time to the tag. This is an absolute timer that is incremented every millisecond. All the tags associated to the same access point will share the same absolute time, running aligned with the absolute timer in the access point. Beside this, the access point sync key material will be transferred to the tag. This is a global key used to encrypt all commands sent from the access point to the tags over PAwR. The access point shares this key to the tag so that the tag will be able to decrypt commands from the access point later on. In addition to this, the access point will generate and write a unique response key for this specific tag. When a tag responds back to the access point on a response lot on PAwR, the tag will use this response key to encrypt its response, and the access point will use it to decrypt it. In addition to this, the access point will also write into the ESL the ESL address specific to that tag. This is a unique address for each tag. It's not the Bluetooth address. This ESL address is a specific address, I would say an application logic address. We will go into the details more later on in this presentation. While on a connection, it's also possible for the access point to send display images using the object transfer service. Once all of this has been completed and the access point has written all the mandatory characteristics, the access point will then transfer the synchronization to the tag using the periodic advertising sync transfer procedure. It's good to note that even if for PAwR there are different ways for a scanner to get synchronized to an advertiser, for Bluetooth ESL, the only way for a tag to synchronize to an access point is by using a periodic advertising sync transfer procedure, a PAST procedure. Using this PAST procedure, the tag receives the synchronization information, which includes the PAwR parameters, and tells to the tag where to find the PAwR synchronization packets coming from the access point. The tag can then move to the synchronized state and subscribe to the write PAwR subevent. In this state, the tag is a PAwR scanner. That means it's synchronized to a specific subevent. It will wake up every periodic advertising interval. It receives the subevent packet from the access point. It interprets this packet, and if needed, it will send a response back before going to sleep. This is a connectionless status, as discussed earlier. The ESL address plays an important role here because it is used for the tag to understand to which subevent it needs to subscribe and to which group it belongs to. So let's have a look what the ESL address is. The ESL address is made of two different parameters. The group ID, which is 7 bits, and the ESL ID, which is 8 bits. The group ID corresponds to the sub-event to which the tag needs to be synchronized to. So, as soon as the tag receives the passed procedure, so that receives the synchronization from the access point, the tag will check the ESL address written by the access point during the ACL connection. It will check the group ID field and is synchronized to the corresponding sub-event. So if, for example, this first tag has received the address 0000, in this case, it means that it has been assigned to the group 0, and the ESL ID is also 0. This tag will therefore synchronize to the sub-event 0 corresponding to group ID 0. Remember that there are in PAwR a maximum of 128 sub-events for each PA interval. So also in ESL standard there are a maximum of 128 groups, as you can see here. That is why the group ID field is only 7 bits. And there is a one-to-one mapping between sub-events and group IDs. However, it is up to the access point to decide how many groups to use, how many sub-events to use for each implementation. And it's the access point that then will assign the ESL addresses accordingly to the tags. And how many tags can we have for each group? Within each group, you can have 255 tags with a unique address. This is because you have 8 bits for the ESL ID, and therefore 256 ESL IDs. However, one of these cannot be assigned to any tag. So, totally, 255 is the number of actual available ESL ID addresses per each group to be assigned to the tags. The last ESL ID address, specifically FF0xFF, is used only for broadcast messages, as we will see later. Note that the ESL address is meant to be unique for each operating tag, so the access point should have smart logics in place to prevent two synchronized tags to have the same ESL address. Following the same procedure, the access point can associate more tags and bring them to synchronized state. For example, in this case, the access point has connected to another tag, this one for example, and it has assigned another address, which is 00 for the group ID and 01 for the ESL ID. This tag then receives the synchronization from the access point. The tags, as mentioned before, reads the group ID and synchronize to the sub-event 0 corresponding to the group ID 0. And indeed, as you can see, this tag has been placed on the group 0. And now we have another tag, and so on. One after the other, the access point can add the tags. It's the access point that decides which address to assign to each tag at any given time. And therefore, it's the access point that decides by doing this to which group each tag will fall into. For example, we can see that the yellow tag here has received a different address which has a different group ID 1. And so the tag automatically will subscribe and synchronize to this subevent 1, and the tag will now belong to the group 1. When you have tags in synchronized state, they can receive commands and send responses back over PAwR. You can start doing so as soon as you have at least one tag synchronized to access point. Indeed, the procedure to associate tags can be done at any time while the access point is up and running and operational, while sending commands and receiving responses over PAwR. The synchronized state is the most important one. This is where all the magic happens. This is where the tag is leveraging PAwR to receive commands and send the response back. The tags will spend most of their lifetime in this state. So let's say that we have several tags that are in the group 0, the first group. These tags are in synchronized state and subscribed to subevent 0. Now the tags in this group can wake up at the right time and can receive commands from the access point included in the payload of the advertising packet in subevent 0. The tags can then respond in some specific response slots and then go back to sleep. The access point then will send other commands in subevent 1 addressing group 1. And here we have all the tags in group 1 waking up, processing the commands, and sending responses back if needed, and then going back to sleep. How many response slots do we have for this application? This is decided by the access point. The access point sets the timing of the PAwR, the number of subevents, the number of response slots available. Such details are given to the tags from the access point when the synchronization is passed to the tags. Once these parameters are set, the access point is already sending the train of subevents, and it's clear that the access point should never change the PAwR timings at runtime, otherwise all tags will lose synchronization. Such PAwR parameters have implications on upper layer logics, for example on the number of commands that can be included on the same subevent. The access point should keep this into account when sending commands, as we will see later. Let's now focus in understanding how the Bluetooth ESL spec tells us to structure the packets to be included in each subevent, so that we can send commands to multiple tags in each specific group. In this example, we want to send some commands to more tags in group 0. These commands are included in the ESL payload. We need to include this payload in the advertising packet of subevent 0. However, our payload needs to be encrypted using the Bluetooth 5.4 feature, the encrypted advertising data type. The key used to encrypt the payload is the access point sync key material. This key is used to encrypt all the commands sent to all the groups from the access point. However, how do we exactly build up the ESL payload that we want to then encrypt and send in the subevent? This is specified in the Bluetooth ESL standard. First, to keep in mind, the maximum payload for the ESL is 48 bytes. Note that the maximum payload of the advertising packet on the sub-event in PAwR can be larger, but for ESL, the maximum payload has been set and chosen to be 48 byte. So what do we include in this payload? How do we specify the commands to the tags? First of all, the ESL payload includes the group ID. So in this case, we want to send a message to tags in group 0, so we will write in this field group 0. This is a redundancy mechanism to make sure that only tags in group 0 will process such payload. If by accident a tag belonging to another group receives this payload, it can simply ignore it because it doesn't belong to the specified group. After the group 0, we have TLVs. TLVs are the actual commands that are sent to one or more tags in this group. TLV stands for tag length value. Each TLV is built by an opcode and some parameters. The opcode is 1 byte in length, and we have a list of available opcodes in the spec corresponding to the commands that the access point can send to the tags. An opcode is defining each of these commands. For example, for the ping, we have opcode 00. In this case, the ping will only allow the access point to ping a specific tag and receive a basic status information from the tag. However, for example, if you want to change the image displayed on the ESL, you need to use another opcode, as you can see in the table. In this case, the tag already has some images stored, and the access point is using this command to request the display to the ESL to display an image, for example, image 0, image 1, or image 2, and so on. You can also implement custom vendor-specific commands. Please note that the opcode includes two fields, one being the tag and one being the length information. We will see what it means later. Now let's look at a real example. Let's say that we want to send the following command to some specific tags in group 0. As a reminder, we are assuming that the tags are already in synchronized state. So they are all synchronized and they can wake up at the right sub-event and listen to these commands from the access point. In this case, for example, we want to ping the tag with ESL ID 4, and we want to ping it, and so we want to check if the tag, for example, is still alive, is everything okay, or if it has any error. And we will include this command in the first TLV number 1. Since we can address multiple tags with one ESL payload, we have indeed 48 bytes available, and we have multiple response slots available, we can send other TLVs addressing other tags in the same group. In this example, we want to ping tag number 2, and this will be the second TLV. But for the same tag, again, tag number 2, tag with ESL ID 02, we want to change also the image. We want to display a different image. We want to display the image with image index number 1. And this will be the third TLV, TLV number 3. So now we'll see how this TLV should look like in the following slide. For the first TLV, we want to ping tag number 4. So we know all the opcodes for all the commands in the standard. We have seen the table before, and we go there and check which is the right opcode for the ping command. As you can see here, the right opcode is 0x00, and we place this opcode in the first field of the TLV. After that, we have the field of the parameters. Here, it is interesting to know that the length of the parameter is defined to be the length component of the opcode plus 1 byte. As a consequence, the total TLV length is the length in the opcode plus 2 bytes. This is because the opcode itself is 1 byte. In this case, we have a length of 0, as you can see here. The length is 0. So the parameter will only be 1 byte long, and the total TLV will be 2 bytes. So we know that the parameter will need to be 1 byte long. So what do we need to put as a parameter? Well, we want to ping tag number 4 in group 0. So it is obvious that the parameters in this case needs to be the ESL ID of the tag that we want to ping, in this case 0x04, so the tag number 4. And however, when choosing the parameters, we need to look into the standard. It's the spec that tells us which parameter to use in combination with each opcode. As you can see here on the table, we have a parameter specified for the ping, and this parameter is the ESL ID. So what we include here on the parameter field is the ESL ID of the tag we want to ping in this group, which is tag number 4. We have built the first TLV, the first command that we will include in the sub-event of the periodic advertise with response, going to address the tags in group 0. Now we want to ping the tag number 2 in the same group. So it's the same command, similar command as before, it's a ping command, but in this case, since we want to ping tag number 2, we specify 2 in the parameter field. And this is the second TLV. For the third TLV, we want to do something different. In this case, we want to change the image on the ESL display. So we need to check the opcode for this command in the spec. And as mentioned before, the opcode is 20. And what about the parameters? So we write this opcode here, and we need to decide then the parameters. And for the parameters, once again, we need to go and check the service documentation. The service says that the parameter format for this command is made of 3 octets. The field number 1 is the ESL ID, the second is the display index, and the last is the image index. What does it mean? Of course, we need to have the ESL ID here because we want to say which tag needs to execute this command. So the first parameter will the first component of the parameter will be 2 because we want to address tag number 2 in this example. This is here. Then we have a display index. In this case, let's assume that the tag has only one display, so this will be display number 0. And for the image index, let's assume that we have already transferred different images to this ESL tag during the last ACL connection with access point. Each of these images are stored in the tag with an index. In this command, we need to indicate which image index we want that the tag will display. And in this case, we just for example, we want to say that we want to display image number 1. And so we will write it here. Let's just check that it makes sense. And we can verify, for example, that the length of the parameter is correct. The total length of the parameter field is equal, as we've seen before, to the length parameter of the opcode, in this case it's 2, plus 1 byte, so total 3 bytes. And this is correct as we have a parameter field of 3 bytes and total TLV is 4 bytes. So this is the third TLV that we want to send in sub event 0. And these are all the TLVs that together with the group ID will build up our ESL payload. If we wanted, we could have sent even more TLVs in this sync packet. So the question is, how many TLVs, how many commands can we include in general in one ESL payload? This depends on the TLV size. As you can see, some TLVs, for example the ping, are very short. Others are longer. And the maximum ESL payload is always 48 bytes. So if you have very long TLVs, of course you can send less TLVs at the same time, so less commands at the same times. But beside this, the access point needs to keep in mind how many response slots are available, because on the, depending on the number of TLVs, you may need a different number of response slots available. So it's the access point responsibility to specify, to include in the ESL payload the TLVs in a way that the tags have a response slot available to respond back. So the bottom line is that you need to keep in mind the number of response slots available and the maximum payload when sending commands from the access point. Now that we have built the ESL payload, this will be encrypted and sent to the right group. So all the tags that are synchronized on the first group, group 0, will wake up, listen to this sub-event sync packet. After decrypting the payload, each tag will check all these parameters to see if it needs to execute any command. Each tag in the group basically needs to see if there is its own ESL ID in the parameter fields, or if there is a broadcast address in the parameter field. In this example, only tag number 4 and then tag number 2 are receiving commands. All other tags will go through the ESL payload, but they have not received any command, any TLV. And so all the other tags will go back to sleep immediately. So only tag number 2 and tag number 4 will have to send back a response to the access point. How does it work, the response behavior? The assignment of response slots is dynamic. Each tag needs to decide on which response slot to reply at runtime in order to avoid collisions with other tags. This is done by some rules specified in the Bluetooth ESL spec. So these are upper layer logics that determine how this assignment of response slots is done for each ESL payload. You can find these rules in the profile spec. Now we will not go through all these rules, and there are several kernel cases that needs to be taken into account depending on the commands. Here we want to mention only rule number 3 and 4 because these are the one relevant for this example. But this is not always the case. So please feel free to pause the video and read these two rules now, rule number 3 and 4, to understand how each tag should decide in which response slot to reply. Based on rule number 4, the tag number 4 has received only one TLV, and this was the first TLV in the ESL payload. And based on rule number 4, the tag number 4 will then use the first response slot to reply back to the access point. This is because it was the first TLV, and so the tag in the first TLV will reply back on the first response slot. The tag number 2 instead received 2 TLVs. So in this case, there are two rules that apply, that are rule number 3 and rule number 4. The tag number 2 indeed received commands in the second TLV and in the third TLV. Based on the rules in the spec, the tag needs to reply on the last response slot in which the tag has been included in a TLV. So for example, in this case, the tag has been included in TLV, in the second TLV, in the third TLV, so it will be the last TLV that will matter, and the tag will need to reply on the third response slot. Even if it seems complicated, the good news is that in the Nordic implementation of the tags, we take care of this. However, it's important to understand the logics. Indeed, on the access point, you will be the one sending TLVs, and so you need to understand in which response slot you expect a response from which tag. Once the tag decides where to reply back, it needs to build up the ESL payload to be included in the advertising packet of the response. Also in this case, the ESL payload will be encrypted using the unique ESL response key material. So each tag has its own key response it has its own response key, as we have discussed earlier. And also in this case, the ESL payload has a maximum limit to 48 bytes. So the structure of the responses is very similar to the ones on the commands, with the difference that in this case there is no group ID in the ESL payload. This is because the access point will get its information from the Bluetooth stack directly, so the access point will know for which sub-event the response has been received. Also in this case, when the tag replies back, you can have multiple TLVs, multiple messages. And this is because the tag may have received multiple commands, as we have seen in this case. This tag number 2, has received 2 commands. For this example, we will just see how to build the response for the first TLV received by this tag. In this case, the first TLV received by the tag was a ping command. So we can see how to structure a response, a TLV, for a ping command. The TLV is pretty similar to what we have seen before. So we have an opcode and a parameter. Which opcode and which parameter to be used depend on the command. So for each command, there is a mandatory response behavior. So, for example, for the ping command, we shall reply with a basic state response. So we can check in the spec, and the opcode for the basic state response is 0x10. And then for the basic state, we have a table on how to build the parameter field. In this case, we know that the tag is synchronized. So this will translate into the parameter shown here in the presentation, after converting the binary number to the hexadecimal. Once the tag has built the ESL payload for the response with all the TLVs, it will encrypt it and send back to the access point in the right response slots as we have seen. The access point will decrypt the message and interpret the message. All what we have seen now is a connectionless mechanism to send commands to tags and receive responses. So all of this is done using the PAwR mechanism in combination with the EAD feature to encrypt the commands and the responses. So now we will go through some other interesting features and concept of Bluetooth ESL. As mentioned before, the access point and all the tags share the same absolute time. This is a 32-bit absolute time counter with a 1 millisecond resolution. So it's possible to schedule commands up to about 49 days in advance. For example, let's say that we want a tag to display an image in 1 hour from now, independently from the access point. Right now, we can send a timed command over PAwR, which is a command that includes the absolute time at which the tag needs to execute the command. This here is the parameters of the TLV. So we can calculate this absolute time to specify in this TLV as the current absolute time of the system, and we can add to that 1 hour, for example. This absolute time will go into the parameter field of the TLV. When the tag receives this command, it will not execute it, but it will schedule this command to be executed at exactly the absolute time received here. So when the tag reaches this time, it will execute the command independently from the access point. This feature can be quite powerful when you want all the tags to do something or many tags to do something at the same time and schedule a command for many tags that needs to happen exactly at the same time. For example, change all the prices at 8 o'clock in the evening or so. Another interesting feature is how to send a command to all the tags in a specific group, so that all tags in that group, only that group, should execute it. This is simply done by specifying the broadcast address FF as ESL ID in the TLV. In the example seen before, if, for example, we want all the tags in group 0 to change display image, we can do it as shown here. We can include the ESL ID in the parameter, and in this case we choose FF. All tags will then wake up and will see this ESL ID in the parameter field, and all of them in that group will execute the command and then go back to sleep without sending any response back. So far we have seen the tags from unassociated. We went to configuring, and then we have seen how to synchronize the tags, and then we have seen operations in the synchronized state, mainly sending and receiving commands. But from time to time, the access point may want to connect directly to a specific tag while keeping sending commands to all the others. The access point can do this in ESL, in Bluetooth ESL, and this is done by moving the tag to the updating state, so establishing a connection with the tag. This can be done by access point including such a connection request directly in one of these sub-events. So it's possible to include, instead of a payload, we can include a connection request to a specific tag in the sub-event. Once the tag is connected, it will move to the updating state. As you can see, this is a very optimized way to establish a connection with a synchronized tag. Naturally, in this case, in the case of Bluetooth ESL, we assume that already both devices have already kept the bonds from the previous pairing, so they just need to connect and the connection is already encrypted. Once the tag is in this state, the tag can still be controlled by the access point using the so-called ESL control point characteristics, which allows the access point to send and receive responses with the same structure that we have seen before, but now it's by reading and writing characteristic. Besides this, in this state, the tag can receive new images to store for future use of the display. And to transfer these images, again, the object transfer service needs to be used. After all these procedures, all these operations in the connection state are completed, the access point must notify that the update procedure has completed. And following that, the access point needs to trigger also the pass procedure to allow the tag to regain synchronization and move back to the synchronized state. From this state, however, the access point can also force the tag to go to unassociated. If so, the tag will need to reset all the parameters and forget the bonds and the keys, and it will be ready for being associated again from the same access point or another access point. Another important aspect of the state machine is that the tag may lose the synchronization from a PAwR point of view or from a Bluetooth ESL point of view. From a Bluetooth ESL point of view, it's important to remember that if a tag does not resolve a command within 1 hour, the tag needs to move to unsynchronized state. Please pause the video to read which are the timers that affect this and in which other case the tag may lose synchronization at Bluetooth level. When unsynchronized, the tag will be advertising in the advertising channel. Similar to the unassociated, but in this case, the tag can connect only to the access point previously associated with. If another access point tries to connect to this tag, the tag will reject the connection. So only the associated access point can scan and connect to the tag. The tag will then move to updating state, as we have seen in the previous slide. When in the unsynchronized state, the tag keeps all the bonds and keys that have been set during the configuring state, and this is the major difference with the unassociated state as well. There is another important timeout which is not shown here in the state machine, but it's in the spec. If the tag stays for 1 hour in the unsynchronized state, after 1 hour, the tag must move to unassociate. So any access point can connect to it. This timeout is quite interesting because it allows tags to move within a store, within a warehouse, and hence it can associate to different tags in case it has moved. From an access point of view, the spec leaves a lot of flexibility. It is up to each access point implementation on how to handle the Bluetooth ESL tags. The spec indeed focuses mainly on the tag behavior and only indirectly on the access point. In this slide, you will find some valuable information on how the access point should handle the tags and understand their status. It is good to know how the access point should prevent the tags to lose synchronization, for example, by sending pings from time to time, and how the access point can understand if the tag is still synchronized, or it is in unsynchronized state, or it is in unassociated. So feel free to pause the video if you want to read the details here. With this, we have covered the entire state machine and behavior of the Bluetooth ESL, and it's time to see the Bluetooth ESL in action on a real setup. Now let's see a demo to help us visualize all the concepts that we have seen so far. In this demo, there is an access point. This is implemented on an RF5340 development kit. This has been preloaded with manual onboarding access point application by Nordic. This access point is operated from the PC using a shell command interface over USB. Then we have several tags that have been already associated to the access point and are already synchronized to the PAwR sync packets. We have 8 Thingy 52, one nRF52833 development kit, one menu tag, one custom board with an nRF52840 dongle and a large EPD display, and we want to add a new tag, the nRF52833 development kit with a small EPD display. All of this is based on RF Connect SDK and the Bluetooth ESL application by Nordic. The step-by-step guide to replicate this demo is provided in the Nordic Bluetooth ESL tutorial, which we will mention at the end of the presentation. Let's now have a closer look to the setup. As you can see, we have an access point which is on the bottom right corner. And then we have already several tags that have been associated and are synchronized. We have placed the tags in different groups, as you can see in this image. So we have several tags in the first group, group 0, 2 tags in group 1, 2 tags in group 2, and then we have 1 tag in group 30, 1 in group 60, and 1 in group 90. Here we have a new tag that we want to onboard and associate with this access point. So we will go through the state machine for this new tag. Let's now see the devices in the real demo. As you can see, we have an access point on the bottom right of the screen. We have several tags that have been already synchronized, and this at the center is the new tag that we want to associate with the access point. Notice that all the tags that have been already associated are receiving a sync packet from the access point. When this sync packet is received, the LED will blink for a very short period of time. In the dev kit, you have the LED 4 that represent this status LED. The new tag now is in a mode which is called shipping mode. It is in low power state. Now we will wake it up and the tag will start advertising because it is in an unassociated state. To wake it up, we have 2 options. One is to press a button, but the other option we have on RF52 SoCs is to wake it up on NFC, because the NFC functionality is integrated in most of SoCs by Nordic. So we can wake it up by just tapping the smartphone, and you can see that the screen is initializing and LED is starting to blink quite fast, signaling an advertising state. The tag is unassociated. So now we can zoom in into this tag. Notice that the screen is printing the status of the tag and the Bluetooth address. So the tag is unassociated, the LED is blinking, and here is the Bluetooth address. So what we are going to do is now to connect from the access point to this tag. We will use the shell command that you see on the right screen. That is the shell command that is controlling the access point. So we will use some commands to connect to the tag. The tag is connected. We can see that the LED is stable on. There has been a discovery, and now we can configure the tag as we want. As we show in the presentation, we want to add this tag to the first group, group 0, with an ESL ID 02. So we will provide this information to the access point, The access point will configure the tag, reading and writing the mandatory characteristics, including the response key. This is quite important because we will use this response key later for decrypting the responses from this tag. To read this information from this specific tag, we can use another command to provide us all the information. And here you can see, for example, all the information that has been printed. And this is the response key that the access point has assigned to the tag. We can also see that the tag can support up to 2 display images. Please note that while we are doing this procedure, all the other tags are still synchronized and they can receive commands from the access point. We will show that later. Now let's continue to configure the tag. Since it has a display, we want to send, using the object transfer service, new display images. In this case, the access point already has stored some images, so this needs to be transferred to the tag over the connection. Also in this case, we use the shell command to transfer the images. In this case, we have 2 images to transfer, so we do that using the shell command. We can also transfer the absolute time from the access point to the tag, so the tag has the same time as the access point. Once this is completed, we can use the past procedure to let the tag synchronize to the access point. The tag disconnected, and you can see that now the tag has changed the screen. It says that this is now associated with the ESL address that we wanted, and the LED is blinking in a different way because now the tag is in a synchronized mode, and the LED will blink only when the sync packet is received. We associated this tag to the group number 0. So let's put this tag in the right group on the desk just for visualization purposes. Now the tag is associated to the access point, so we can send and receive commands from the access point to the tag, and we will see this in the next few seconds. Before sending the commands, we want to create the TLVs and the commands that needs to be passed to the access point. So we have another tool, which is a Python tool by Nordic, and let's see this tool, which is here on the top corner. This tool will help us build the TLVs, as we have seen earlier in the slides. So let's start with the tag number 4, and let's say that we want to ping this tag. So here we can specify these parameters. So we want to ping the tag number 4 in group 0. So we write, already the group is correct, so we just need to change the tag ID. And we specify here that we want a ping. At this point we can click Add TLV, and the TLV is created for pinging the tag number 4 in group 0. Let's now set up another command for another tag. Let's say that we want to ping the new tag, tag number 2, in the same group. So we just change these parameters, the ping is still here, we can add this TLV. We have seen this in the slides earlier. Now we want to do something else. For the same tag number 2, which is the new tag that we have just added, we want to also display another image. And in this case, you can see we needed to change the parameter here, and it has two fields that we need to configure. One is the display index. According to the Bluetooth ESL, one tag can have multiple displays. In this case, we have only one display, so we keep it as 0. And then we want to display a different image in this case. We want to display image 1. And we click Add TLV. Now we have the complete TLV, similar to what we've seen earlier in the slides. And we want to send this command to the group number 0. In this case, we use the shell command to pass this command from the access point to the tag. By clicking command, the right command for the shell interface is generated. Now we can take this command, copy, and use it in the shell command, and you will see that as soon as we pass this to the access point will send this TLV to group 0 using PAwR. So it will send a command to the tags. Only the tags that have been addressed in these TLVs will read this parameter and take actions. So as you can see, tag number 2 is changing the display image as we wanted. And we can see also that we have received responses by both tags. Just for references, you can see the slide that we have displayed before. And also in that case, we use the same TLV commands sent over the first to the first group, and we received two responses as expected, one in slot 0 and one in slot 2. And this is exactly as we got here. Let's now try to analyze one of the responses, the response in slot 2, to see if it is matching with our expectation. Here we went back to the slide, and we can see what we should expect from this tag number 2 that received 2 TLVs. And we will analyze only the first one. To do this, we need to read the response that we have received from the tag. To do that, we use a command on the access point. And here we get this encrypted response from the tag number 2. And we can now decrypt and see if this is matching with our expectation. We can see another tool from Nordic, which is provided, which is helping to decrypt the responses from the tag. In this case, we use this tool, and the first parameter is the response that we got from the tag number 2, in the response slot 2, and then we use the response key that should be used to decrypt the message. Here we see that we got the decrypted data, which corresponds to the responses received by the access point from the tag. As you can see, this tool returns several parameters. We will not analyze all of them, but we can go through some of this. So the first 2 digits, 07, indicates how many bytes are following. 34 indicates that this is an ESL EAD, encrypted advertising payload. And then we have 2 TLVs, which are the 2 responses to the 2 TLV that we have sent. In this case, we have sent a ping plus a command to change the image. And we can see that the first TLV that we receive here is TLV 100-200. This is exactly what we were expecting from as a response for a ping, as we have seen earlier in the slides. So we have seen how to send commands from the access point to some specific tags, and how the access point receives immediately the responses. They are buffered in our access point, and we can read the content from the access point and decrypt the data. As you can see now, the tags are all synchronized. But at any time, we may want to connect to one specific tag or even more, and perform some operation. For example, we want to send new display images, or we want to configure or set up some parameters. So we will see now how we can actually connect to a specific tag, even if this tag is already synchronized. In this case, we use a command, and we include this command. We send this command over the shell interface, and as you can see, we requested to connect to the tag number 2. We specify the Bluetooth address and the ESL address, and the tag number 2 is now connected to the access point, while all the other tags are kept in synchronization. This is possible because in the sync packet in the PAwR, we can include a connection request to a specific tag. Now the tag is connected, we can send, for example, new images to this tag. But before that, we want to also see that while we are connected to one tag, we can still operate the other tags. And we want to show this. For example, let's say that we want to send a command to the tags in group number 1, and we want to update the images while we are connected to this tag. So we can do this. You will see that the tags will change the display images immediately after we have sent this command. This command has been sent using PAwR, and still we are connected to this tag that we want to configure. So let's keep going, and let's send new images to this tag. So we use similar commands that we used before, but in this case we specify a different image that we want to transfer. Now we want to transfer image 2 and image 3. Image 2 has been transferred. Now we do image 3, and this has been also transferred. At this stage, we want to tell the tag, which is now in updating status here. We want to say that the update procedure is complete, and we have a command for this. As soon as we send this command, the tag goes back to synchronization. However, from a standard point of view, we need to also send another command on the access point, because there could be some tags according to the standard that needs also an extra step to regain the synchronization. In this case, we don't need it. Our tag will pass to synchronized immediately after the update complete. The tag is already synchronized again, as you can see from the status LED. Now, for example, we can update the image on this display, but in this case, instead of using a specific command that, as we have seen before, we will use a predefined command that we have in our access point that will send a message to the tags in the group, in the first group, and we ask the tags to change the image. Unfortunately, the thingy does not have any display, but we simulate the display by blinking the LED in a different way. So we will see it. Let's use this command to address the first group and to change the image. As you can see, the tag has changed the image on the display, and we can do it again, asking to change to image to a different image, because there are two images that have been transferred. So now we will ask to change to the other image, and we can also zoom in to see a bit better. You can see also that the access point received responses to the command from all the tags in the group, in the first group, group 0. Let's put back the tag here. Now we can also do other type of sending other type of commands, and we will play a bit to show other features. For example, we have some LED on all of these tags. Again, we can decide, while all the tags are synchronized, to send the command to group 0 to turn on LEDs. We can do this by using a command. You can see that all the LED got turned on. In this case, also on the dev kit, there are two LEDs. There are LEDs that are indicating that the LED is on. These are specifically LED 1 in each development kit. But we can do this also on other groups. For example, we want to change the LED on the second group. We can, group number 1, we can do it. We can turn the LED on, and you can see that the LED is now on in both cases. Now we can do the same with other groups. For example, we can switch off the first group, and we can do that is again with another command. As you can see, as soon as the command is received over PAwR by the tags process the information and they trigger the action. We can do the same for the second group, and so on. Now let's say that we want to turn on the LED in the group number 30, so we can do that in this case, and we can then switch off the LED again. So all of this is done over PAwR, and we have seen basically all the steps to associate the new tag and to configure it, to send commands and receive responses, and also to reconnect to the tag while this is synchronized. Now that we have understood how Bluetooth ESL works, it's good to spend a few slides on system-level design choices related to the latency of the system. To understand how the timings are interconnected between different parameters, we will start from an example. These are the default timing parameters that have been chosen in the Nordic ESL access point. Of course, each customer can change them, but it's important to keep in mind what it means to change these parameters and what are the implications. How are all these parameters interconnected? Let's go through these parameters. Remember that the access point is the one where this timing information is set. Tags will receive these timings during the synchronization procedure during the past. However, the choice of these parameters will have an impact on the tags, their behavior, their power consumption as well. So it's good to understand how this works. The first one refers to the data rate that we are using. In our example, we have used the 2 megabit per second physical layer, but from a Bluetooth soft device controller point of view, Nordic can support PAwR also with different data rates. It's good to note that if you change these parameters, you will need to change other parameters as well, as we will see later. In terms of PAwR, the PA interval that we have chosen is 1.76 seconds. And actually, this is related to the number of number of sub-events, which is 128, and the sub-event interval, which is 13.75 milliseconds. We will see later that this PA interval will impact the system latency, but of course it also impacts the power consumption of the tags. So if you want to send a message to a tag in group 0, you can do it now in this sub-event, or you can do it later on the next sub-event 0. So you need to wait 1.76 seconds to address tags on the same group. You can, for example, decrease this periodic advertise interval to decrease the latency. This could be done, for example, in combination with a decrease of sub-event intervals or a decrease on the number of sub-events. However, such a choice will have an impact on the number of tags you can handle. And also, by decreasing the PA interval, you will also increase the power consumption of the tags, because the tag will need to wake up more frequently. So if you want to have a bit lower latency, there could be a trade-off in terms of power consumption. Let's move forward to the other parameters. We have seen that the sub-event interval, which is 13.75 milliseconds, and inside this sub-event interval we have set a 10 millisecond response slot delay. We can use this slot to do other things, for scanning, connections, or other things. The tags are also happy to have such a long response slot delay because they have good time to process the commands and send responses back. We have already mentioned that we used 128 groups in our example. This will help us maximize the number of tags we can have in the system. If we use all the sub-events, we can handle more tags, of course. However, for other applications, these may not be the best choice. This depends on what you want to do with your use case. Going forward, we use 8 response slots. Also in this case, there are some trade-offs. You can increase the number of response slots. You can address more tags at the same time within each sub-event for each group by doing that. But at the same time, if you increase this number, after one point you will not get so much benefits anymore, because still you are limited to the maximum payload, ESL payload, that you can send in each sub-event. Moreover, by increasing the number of response slots, you need to give up either on the response slot delay, or you need to increase the overall PA interval by increasing the sub-event interval between each sub-event. This may also increase the latency of the system. The response slot interval in this case have been set to 0.375 milliseconds, which is okay for 2 megabit per second physical layer, as it is quite fast and optimized. But if you change the data rate, or you increase the payload of your responses in case you don't need to comply with Bluetooth ESL, you want to deviate from that, you need to increase also such a response slot. Why we want to mention all of this? This is all important because the timing parameters will impact the responsiveness of the system. And in the next slide we can do an example to understand how all these parameters are related together and how they affect the latency of the system. Then, based on that, you can decide your own parameters for the access point based on your use case. If you have an access point and we want to control 5120 tags, to minimize the overall system latency, it's good practice to have the tags evenly distributed across all the groups. So if we have 128 groups, we will assign 40 tags per each group. Under this assumption, how fast can we send a message to a tag? If we need to send a message to only one tag, the latency is set by the periodic advertising interval. Each tag will wake up every 1.70 seconds, so the best case you will need to wait 1.76 seconds and the tag will receive the command. But what if we want to send more commands and address more tags at the same time? If we have 8 response slots and 128 groups, and assuming 0 packet loss, 0 error rate, so best case scenario, we know that in one PA interval, one periodic advertising interval in 1.76 seconds, we know that all the groups will receive a sync packet with some commands. So how many tags can we address in 1.76 seconds? How many TLVs can we send to different tags in different groups within one periodic advertising interval? The mathematics is simple, and here you can see in the slides how this is done. We can, for example, ping or change images in 1024 different tags within 1.76 seconds. For the commands to request a tag to change the LED pattern, this can be different, and this is due to the fact that the TLV size, the command size, are different compared to a ping command, and so for each sub-event you can address less tags with the same ESL payload of 48 bytes. But overall, it's easy to understand how many tags you can at least ping in each periodic advertising. And the parameters that will set the responsivity on the system are at least 3, as we have seen: the periodic advertising interval, the number of response slots, and the number of groups. However, there is another important number that will set the overall latency of your system, and that is the number of tags per group. If you have more devices in each group than the number of response slots available, then it will take more periodic advertising interval to address all of them. So, for example, in this case we have 40 tags per group. Within one PA interval, we can address individually only 8 of them out of 40, because we only have 8 response slots available, assuming that we don't use a broadcast message. So if we want to address all the 40 tags in each group, let's say that we want to ping all of them, for example, it will take 5 PA intervals. So 5 times 1.76 is 8.8 seconds. So to ping all the devices in the system, so all the 5,000 devices in the best case, it will take around 8.8 seconds, ignoring packet losses. And we could think of this number as a kind of ping system latency. And this is intuitive. If we have more tags than the number of groups times the number of response slots, so if we have more than, for example, 1024 tags in our system, the more tags we add, the longer it takes to address all of them. Because in one PA interval, we can only address 1024 tags. So for small networks, when the total number of tags is less than the number given by the number of groups times the number of response slots. So if the number of tags is less than this, the total number of tags will not have a big impact on the ping latency. So how much time it takes to ping all of them. But if we have more tags than, in this case, 1024, yes, the more tags we add, the longer it will take to ping all of them. But still, using the PAwR, the scale is quite impressive. In less than few seconds, in this case in less than 10 seconds, in 8.8 seconds, we can theoretically address more than 5,000 tags. So we can change the images of more than 5,000 tags in less than 10 seconds. So the goal here of this simple mathematics is to show how all these parameters play a role in determining the latency of the system. And this will help you to tune and set these parameters accordingly and use properly this system. Clearly, if you have many devices, there is a trade-off between latencies and the number of access points. So if you want to have a lower latency, you may need to increase the number of access points so that, for example, you have only 8 devices per each group or less. If you can tolerate higher latency, for example, if you can tolerate that you can ping and change images of all tags within 10 seconds, if that latency is okay with you, then you can have more devices for each access point, and you can have more tags per each group, more than the number of response slots. You can have naturally more devices as long as they are within the radial range of the access point. All of these are indeed design choices that you will need to make when you deploy a system. in some applications, in order to have a wireless coverage on the entire area, you may need to simply add multiple access points. So, how many access points do you really need to deploy? Here are listed 3 major factors that determine the number of access points. As discussed in the previous 2 slides, the latency requirement will put a limit to the number of tags you can handle for each access point. The more tags you have for each access point, the longer the ping latency. Since you can estimate the range of the access point and you know the number of the devices within range, you can ask yourself, if I have all the devices within range associated to a single access point, is the latency okay? If not, you may consider tuning the parameter and increasing the number of access points. Of course, there is an upper limit to the number of devices you can have on each access point. That is the total number of addressable tags. We have seen before, this is slightly more than 32,000 if you use the parameters we have set. So if you use all the groups available in the PAwR. If you hit this number, then definitely you need to deploy another access point to handle the remaining tags or to distribute them evenly across the 2 access points. But in most cases, the density of the devices within range is not so high to reach this upper limit. This brings to the last parameter, which is range. In particular, if you don't have many devices per square meter, range will be the main requirement that will set the minimum number of access points you need to deploy. You can do this by using one of the many available simulation tools available in the market. You can simulate the range and based on that decide where to put the access point. Once that is done, you can then foresee how many devices you will probably have within each access point. And then, based on that, you will see if this system will meet your latency requirements or if you hit the maximum number discussed before. If the latency does not meet your requirements, you will need to deploy more access points. Hope this gives you a framework in order to better understand the system latency and better design your system in a multi access point deployment. Now, after having seen the details on PAwR and Bluetooth ESL and some system level concept about latency, we want to have a look at another simple demo. In this demo, we use Thingy 52s to demonstrate Bluetooth ESL and PAwR in action. And specifically, we can see how a single access point can control more than 60 devices in a connectionless way. The demo is based on an RF Connect SDK in combination with the Bluetooth ESL implementation by Nordic. For the access point, we use a Nordic device with automatic onboarding. This is different to what we have seen before. In the previous demo, the access point was set to manual operation, and from the shell command we were controlling all the phases of the association of the tag. In this demo, instead, the access point will do everything automatically in terms of associating tags. So it will scan the tags, connect to them, configuring them, giving ESL addresses and synchronizing them. This demo is interesting for 2 reasons. First, it shows a higher number of devices, more than 60, all controlled with a single access point. Second, it shows that Bluetooth ESL can be used also for other applications, in particular sensor actuator use cases. The Thingy 52 does not have a display, but still we can use the Bluetooth ESL for this device, and the reason for that is that Bluetooth ESL allows for device to have 0 displays, and it can be used also for Bluetooth for sensor applications. This is quite powerful because you can implement a gateway system with some sensors and you can leverage the state machine logics that are already in the Bluetooth ESL. So now we will play some short recorded videos to see the demo, going through the state machine from an associate to synchronize and then sending some commands after the synchronization. First, as mentioned before, we have all devices advertising because they are all unassociated. We can see in this video that they are advertising and unassociated by looking at the blinking of the LEDs in each of these devices. As you can see, the LED blink quite fast, meaning they are advertising. What happens next is that the access point, which is the device on the video on the right side, which is red, will start the accession procedure. And in this procedure, the access point will associate automatically each tag one by one. The access point connects to a tag, the LED is stable, indicating a connection. The access point configures the device and synchronizes it. After the synchronization, the device will start blinking slowly. It will blink only when it receives a periodic advertised sync packet from the access point from its own group. Meanwhile, the access point will keep scanning and connecting to other tags, repeating the association procedure for all remaining tags. Once all the tags are in synchronized state, the tags will wake up at the right time to receive the sync packet in the right sub-event depending on the group they belong to. And they will blink the LED for a very short time. In this case, we have arranged the tags so that the first row on the top is group number 0. The second row from the top is group number 1, and so on. You can see the nice LED pattern reflecting the sync packets coming from the access point in periodic advertising with responses and reflecting the divisions in groups. All tags are synchronized. Even if there is no connection, we can still control all these devices from the access point. In the first case, we send a broadcast message in sub-event 0 to turn on LED in the first group. In the second case, we send a broadcast message to all tags in group 6. As there is no display, the thingies will blink green to confirm. Finally, we can see that we can send commands to specific tags. So we can see and send the LED commands to only few tags in the first group. After this simple demo, let's see what Nordic Semiconductor provides. The good news is that Nordic has full support for PAwR, EAD, and Bluetooth ESL. Let's start with a lower layer and then go up to the applications. The Nordic Bluetooth 5.4 stack is already available in NRF Connect SDK. This is a highly configurable and flexible, robust, proven in the field and qualified stack. At the heart of this Bluetooth stack, there is the Nordic Soft Device Controller, available in RF Connect SDK. This is fully developed in-house and has been already deployed in billions of devices. This is known for best-in-class interoperability and robustness. It has also some specific features developed by Nordic, such as the multi-link, which allows customers to connect up to 20 devices concurrently to the same central. It has support for concurrent multi-role operation, and it is feature-rich, including the latest asynchronous channel, PAwR, Bluetooth 5.1 direction finding, and so on. All these featuring ultra-low power consumption. The new features coming from Bluetooth 5.4 open up new opportunities for Bluetooth. Whenever you need to collect data or send commands to a medium or large network of devices that are in range within the same access point, while keeping the power consumption down, now developers can use the PAwR available in the Nordic Bluetooth stack. This feature is in addition to the other features already supported by Nordic for different industrial use cases, such as the direction finding, Bluetooth Mesh 1.1, Bluetooth network light control, LE audio, Auracast, and so on. Nordic offers on a one-stop shop for Bluetooth Low Energy. Learning how to use Nordic Bluetooth Low Energy in RF connected SDK opens up doors to many applications leveraging Bluetooth Low Energy. Let's go into more details. PAwR is already supported by Nordic Bluetooth stack since RF Connect SDK 2.4. It is qualified and supported on RF52, 53, and ready for 54 series. It supports both advertiser and scanner, so customers can implement both access point and tags, and all data rates are supported. It's already tested and proven and deployed in the field. The API in the Nordic SDK supports also the new EAD feature for encrypting advertising, and it's easy for your customer to use it to encrypt the payload of the advertising packet on standard advertising or in PAwR. As part of the SDK, Nordic provides simple PAwR examples and a dev zone guide on how to start with PAwR from scratch, bottom up, developing your own custom application. So now let's clarify a few things in relation to the Nordic and RF Connect SDK by looking at these typical customer questions. In which Nordic SDK the new PAwR and Bluetooth 5.4 features are available? PAwR is only available in an RF Connect SDK. An RF Connect SDK is the universal and future-proof SDK by Nordic. It supports an RF 52, 53, 91, 7000 series, RF 21, NPM, and all future products from Nordic, such as the NRF54L and NRF54H series. Now let's look into the second question. Some customers that have already used our SDK have noticed that in the NRF Connect SDK there are two Bluetooth controllers available. So the question is, which one is to be used for PAwR? PAwR, periodic advertising with responses, is supported only by the Nordic Soft Device Controller. This is the world famous Bluetooth link layer, fully developed in-house by Nordic and the default choice in NRF Connect SDK. So it is recommended to use the Nordic Soft Device Controller for Bluetooth related projects, including PAwR and Bluetooth ESL. The Nordic Soft Device Controller is part of the NRF Connect SDK, is the default Bluetooth controller in NRF Connect SDK, is fully maintained, qualified, and tested by Nordic in combination with the Bluetooth host at every NRF Connect SDK releases. Let's now move to upper layers, and we will discuss both about application layers and supported hardware. In case you want to implement a Bluetooth ESL tag application, or if you want to get inspired by this and leverage it for your application, Nordic provides a complete example for both tag and access point. So let's now start from the tags. As mentioned, a complete reference example for Bluetooth ESL is offered by Nordic. It includes source code, a getting started kit with a simple tutorial to go from zero up to designing your own tag. It provides two different types of drivers for electronic paper displays, a driver based on the Zephyr display drivers and custom of 3 drivers. It includes the Bluetooth ESL service and profile implementation, and this is support on multiple SOCs including 52833 and 52840 and ready for 54 using the same code base. We provide also different file systems to handle different type of images, smaller and larger display images. When it comes to hardware, Nordic provides all it needed to create a tag. Using the Nordic SoC, it's easy to combine the Nordic reference design with third-party displays reference designs to build your custom board. The high level of integration of Nordic SoC means reduced bill of material and lower cost for the entire product. As we have seen in one of the previous demo, a tag can be built from as little as a Nordic nRF52840 dongle. Then, using the SPI interface, you can connect displays or external flash or sensors. The antenna can be integrated on a PCB using the Nordic help, and you can use also two-layer PCB for further reducing costs. It's possible to drive the Nordic SoC directly from coin cells, and most Nordic SoC include also NFC tag functionalities for free, which can be quite useful for user interaction. To build quickly a proof of concept, it's possible to start directly from the Nordic Dev Kit, as you will see in the next slide, or by using third-party modules embedding the Nordic SoCs. To get started with the tag is very simple. You can try the entire Bluetooth ESL implementation on a simple nRF52833 development kit. This means that you can use these as it is. Even if you don't have a display, you can test most of the functionalities, most important features of Bluetooth ESL. And we will see this at the end of this presentation in another demo. However, if you want to add a display to see the full demo or to play around, we support two displays out of the box with a shield to plug on top of the DK. If you want to measure also power consumption, you can use the Nordic Power Profiler Kit 2, as we will see in the last demo. It is important to emphasize that Nordic provides a broad offering of SoCs to meet different use cases and different customers' needs. Nordic SoCs have already been deployed in very high volumes in ESL applications. Here there are some SoCs that can be used for Bluetooth ESL, including the new nRF54L15. While recording this training, the nRF54L15 is currently in limited sampling and will go in mass production soon. More SoCs are coming from Nordic into the market, so please keep in touch with Nordic, either directly with the Nordic sales representative or using the Nordic news, so you can know the latest on Nordic products, roadmap and pricing. Here are some of the advantages of using a Nordic SoCs in your ESL application. Nordic provides best-in-class multi-protocol and flexible radio, featuring low power consumption for extended battery lifetime of your product. You can choose to use the Nordic SoC with proprietary features or using the Nordic Bluetooth 5.4 stack or mixing and match with other technologies. For example, you can mix and match the Nordic implementation with other technologies such as the direction finding, 5.1 AOA AOD, or other proprietary phase-based distance measurements named Nordic Distance Toolbox. Nordic provides high level of integration, so you can have a very optimized bill of material, end-to-end support from software sample, trainings, technical support, so that you can go to market as fast as possible. Nordic provides overall an open approach, so most tools and software are open source, and many of the components and software also tools are providing full source code. Finally, Nordic provides a scalable platform so that the customers can scale up or down their application, porting across different SoCs with minimum effort and therefore optimizing cost. As you can see from this table, the Bluetooth PAwR fits quite well and can run quite well in several SoCs. However, given the RAM and flash requirements, for Bluetooth ESL it's suggested to start with the nRF52833 and then scale up or down to different SoCs depending on your needs. The advantage of this approach is that you can start already today developing the Bluetooth ESL tag using the nRF52 series in production. For example, you can use the nRF52833, and then as soon as the 54L series is available, you can move to the nRF54L series. The nRF54L series brings more non-volatile memory, more RAM, it has improved radio, it has lower power consumption, more security features, higher level of integration, an extra RISC-V core, and it's more price competitive. Both SoCs are supported by the nRF Connect SDK, so you don't need to wait for the nRF54 series to start playing with the Bluetooth ESL implementation. The development can start now, for example, on nRF52833 or 52840, and then move easily to nRF54L series. Let's now move to the access point. Nordic provides a serialized access point. It means full Bluetooth stack, and the access point central application are running on the nRF53 SoC. However, this is serialized over USB. It means that it exposes a shell command interface to the host PC, abstracting most of the complexity as we have seen in the demo before. The software can run on an nRF5340 development kit, but can also run on the Thingy 53 for a more compact design. The 53 series has been chosen because it has plenty of flash and RAM, and because it is dual core, so the radio can operate efficiently, independently from the application. Such an implementation allows customers to test and develop the Bluetooth ESL tags easily and without any coding on the access point. It's super easy to use the access point by simply using some of the shell commands to perform all the action from the access point of view. In general, it's good to know that the access point is quite complex. Indeed, in the Bluetooth ESL implementation, it's not fully and directly specified by Bluetooth SIG. That's why Nordic provides the source code so that customers can decide many choices and logics by themselves and modify the code. The goal for Nordic for the access point is to deliver an experimental sample to customers to enable them with testing and development of tags easily. However, this can be also a good starting point for a fully featured access point for ESL or other applications. This access point comes in two operating modes. One is the automatic association of tags, mainly for testing and out-of-the-box experience, and we will see this at the end of this training on the final demo. And one is in manual operation, when a host PC has full control on all the operations of the access point. Both these operations of the access point are explained in the Nordic Bluetooth ESL tutorial, and more information on this are provided at the end of this presentation. Naturally, for customers that want to innovate, there is also the option to use nRF54H20 as a single chip mini access point architecture. Also, this new SoC is currently under limited sampling, so if you are interested in more on this, please contact Nordic. This SoC is a multi-core SoC featuring 2 ARM cores and 2 RISC-V cores available to the developers. It introduces more processing power, more efficiency without compromising the power consumption, and therefore it fits quite well for gateway applications, as it can be used for implementing a single chip fully integrated mini access point. It can be lower cost and easier to use compared to a Linux-based access point. It's also quite modular from a backend connectivity point of view. It's possible to connect the NRF54H20, for example, with an NRF 7002 to add Wi-Fi connectivity, or to add a third-party Ethernet IC for Ethernet, or an NRF 91 for adding cellular connectivity. All of them can be handled by the same BSD socket API, and the drivers are taken care by Nordic in the NRF Connect SDK. There is one last point that can be relevant to customers who want to go fast to market. Many developers may have never used Nordic SoCs, or they may never have used the Nordic NRF Connect SDK. Nordic provides a lot of tools and software to bring product to markets based on the PAwR feature or on Bluetooth ESL for both tags and access point. But there is more than that. To make the journey very smooth, Nordic provides a set of trainings to get up to speed quickly with the NRF Connect SDK and with the Bluetooth API. The Dev Academy is a platform where Nordic delivers free step-by-step online courses open to everyone who wants to learn and develop their skills. You decide the pace at which you follow these courses. Each course is around 8 hours. Within just few hours, therefore, with a very structured training, you can get familiar with most important concepts needed to develop an application with Nordic and to go to production. For Bluetooth ESL, we strongly recommend that you attend at least the following courses: the NRF Connect Fundamentals, the NRF Connect SDK Intermediate, and the Bluetooth Low Energy Fundamentals. The Bluetooth Low Energy Fundamentals course focuses a lot on Bluetooth API. All these courses are recommended for customers who want to use Nordic SoCs in Bluetooth Low Energy project. And these are recommended also to those Nordic customers who have already used Nordic SoCs in the past with the old SDK, and now they want to take advantage of all the new features available in the NRF Connect SDK, and they want to be ready to use also the NRF 54 series as soon as available. Now, after having seen the Nordic offering for Bluetooth ESL, we can see how everybody can learn more, get started quickly with this technology, and to bring to market fast new products based on PAwR and Bluetooth ESL. Whenever you want to handle many devices with a single access point, whether it is 10 or 10,000, it's worth to consider using PAwR for your application. This is even better than designing your own proprietary protocol between gateways and tags. Now you can take advantage of the Bluetooth technology, its robustness, its security, its low power consumption, and the available hardware and software provided by Nordic. In this way, you can focus on your application and your core business. With Nordic, this is easy. We have seen that these technologies can run on 52, 53, 54 series. The qualified Bluetooth stack is available already now in the NRF Connect SDK, and Nordic provides valuable samples to enable different approaches. If you want to have a bottom-up approach, you can start from a Bluetooth PAwR examples from our SDK, and then you can build on top of that. This is good if you want to do something specific or that deviates from the ESL sensor use case. You can really play with all the numbers of sub-events, response slots, and use the radio resources in new ways to enable new applications, including multi-protocol. And more importantly, you can contact Nordic directly, and we can support you to see how best tune the PAwR for your needs. As an alternative, you can choose a top-down approach where you can use the Bluetooth ESL application provided by Nordic. You can use it as it is, or you can reuse some of the components and modify them to your needs to build any application you want. The source code is public. The good news is that we have made the development journey very easy. Indeed, it's easy to get started and build up complexity. Indeed, we have created a Nordic Bluetooth ESL Getting Started Kit. The idea is to have one place where to get started with this technology. This includes a Nordic Bluetooth ESL tutorial, which includes a step-by-step guide to get started, to learn the basics, and to do a simple demo without writing any code. We'll see this demo in just a few seconds. In section 4 of the tutorial, there are a lot of links to documentation, code specification, links to additional PAwR trainings by Nordic or by third parties. Plus, there are links to how-to guides to help you design your product from scratch, both for hardware and software, and go into production. The code is provided within the kit. Moreover, you will find other Python tools that you can use, for example, to generate TLVs, to decrypt responses from tags, or to convert images for electronic paper displays. But there is more than that. We also provide in the kit the precompiled hex files to replicate all our demo that we have seen so far in this training, and in the Bluetooth ESL tutorial there is detailed step-by-step instructions. In the tutorial, we also added a lot of extra valuable information useful for the development. For example, how to enable logs on both access points and tags, how to install the SDK, how to build the code by yourself, plus a section about display drivers and how to create a custom board. So you will learn to use the code that is provided by Nordic. You can run it on the development kit, and you can run it as well on your custom code, and you will learn how to do it by following the tutorial. So you can decide your own specific hardware and port the code easily, since the entire implementation is hardware agnostic from a software point of view. And later you can also run the same application and port it to the 54L as well. In the Bluetooth ESL tutorial by Nordic, we also provide other tricks, for example, on how to do simple current measurements on a development kit using a PAwR Profiler Kit 2, or on a current measurement on a custom board. And we also provide instruction on how to flash custom boards easily using the Nordic dev kits as a programmer. As mentioned before, as part of the tutorial, there is a getting started demo. For this demo, you need one access point. In this case, it's an RF5340 development kit. This is flashed with an application provided by Nordic, and it's included in the getting started kit. In this case, we use an automatic onboarding procedure for the access point. We will see what it means in few seconds. Then you need some dev kits for the tags running the PAwR and the Bluetooth ESL application by Nordic. In this case, we have 3 development kits, but you can use more than that. One standard NRF52833 development kit with a simulated display on LED. One NRF52833 development kit with a shield and a small EPD display. And this will be connected to a PAwR Profiler kit. Then we have a 52833 development kit with a large display. The goal of this demo is to get familiar with some of the concepts and tools presented in the training. This will guarantee a smooth journey to understand and learn better Bluetooth ESL. The Nordic Bluetooth ESL tutorial goes into details on how to replicate this demo and how to expand it with more complex topics. Just one final note on the automatic onboarding procedure of the access point. In this demo, the access point will handle all the association of tags automatically. So you can you cannot decide in this case which address to assign to each of the tags. If you want to do that, you need to use the access point manual onboarding mode, which was presented earlier in the first demo. In this case, indeed, we want to keep the things simple, and therefore we use the automatic operation on the access point. The access point has been preloaded with some display images for different tags. How to do it is also explained in the tutorial. So the access point will scan automatically for the devices with for the tags that are advertising with a ESL service, will connect to each tag one by one and will configure each tag with a ESL address, and will transfer the right images to each tag, and finally will synchronize them. Once that is completed, we can send commands to the tags and receive responses. So now let's see this on a real live demo. Here we have the setup as described. We have a one access point with the shell command. In this case, we will not use much the shell command, but we still use it for keeping an eye on what's going on in the access point. Then we have three tags. These three tags are currently in ship mode, so it means that they consume less than 1 microampere. They don't advertise, they are sleeping, ready to be waken up and to be deployed, let's say. We have one with a small display, one with a large display, and one without the display. In this case, we are powered with a coin cell, and in the other cases, we have a connection to the over USB for the power only. This is only for the power, and actually here we have activated the power measurements on this development kit. How to do it is explained also on our tutorial, and we will see the power consumption here on this kit. So now we will start the demo, and to start the demo we need to activate this automatic onboarding on the access point. This has a different firmware compared to the demo that we have seen before. It's a firmware with this feature enabled, and we will press button 1 to start this feature, and as you can see, the LED started to blink. It means that the access point started to scan for devices advertising with the ESL service. Now we want to activate these tags. We will do the first one here with NFC. Let's see if we get it. Yes, we just tapped the phone, and the tag is now up, and we actually can see this also on the PAwR Profiler kit. So we will see here that the device started to advertise. It has connected, it is sending the images, and it is now associated, and now it's going to since it's got synchronization, it will start waking up only when it needs to receive a synchronization packet. We can see it also on the what happened here. We can stop this and we can go back and see a bit more what happened. So yes, we can see that when we use the NFC, the tag was waking up, and the display got initialized, and at the beginning the display was showing an image saying it was unassociated, and it started to advertise, as you can see here. These are any events where the tag is advertising. At this point, you can see also on the shell command that the access point scanned a tag. This is the tag that has been scanned. We have scanned the tag, it has connected to the tag, it did the discovery, it configured an address. The address is in this case 0000, so this is the Bluetooth ESL address. It transfers also some images, because this tag can support two display images, so the access point based on the vid and PID has transferred the image. We can see this happening also on the logs, and then the access point will provide the synchronization to the tag. The tag will disconnect and will start being synchronized to the access point. At this stage, the tag will change the information in the display. You can see now that the tag is associated with a specific Bluetooth ESL address, and in this last section, this is where the display has changed the status to this new one that is now currently on the display. Now we'll let the measurement going, and we will see exactly what is going on. As you can see, the tag is waking up around every let's see, this is around oops, we need to stop it, around 1.7-1.8 seconds. This is the periodic advertised interval in this case, and the tag is waking up for a very short period of time, and then after it wakes up, it listens for a synchronization packet from the access point, and then it goes back to sleep. So we can see that average current here is around, we can see it, we are around 5 microampere. We can let it run to get more samples, and we can see that the current consumption is around between 4 and 5 microampere generally. While we do this, we can activate now the next tags. The access point is still scanning. We can see it from the LED is still active, so we will wake it up. Also in this case, we can do using the we can do it over NFC. Let's see, and the tag, as soon as we approach with NFC, wakes up, and the LED start blinking here, indicating it's advertising. It's now connected. You can see that it's connected to the access point. Now it will take a bit longer because we are transferring the images, and these images are slightly larger because the display is a bit larger. The images is transferred. Now the procedure is completed. The past procedure took place, and the tag got the synchronization information. Also in this case, the tag has been assigned by the access point to the group 0. We can see it here, but the address is the ESL ID address is 01. So this is the second tag we have in the same group. So you can see also in the display we have this information. The tag is associated, and we have the ESL address here. You can see on the LED 4, it's blinking slowly and indicating this is synchronized. In this case, we don't have LED because we are performing power measurement, and so we have removed for a second the LED light here. Notice that we have done all of this, association of this new tag, while the previous tag was still receiving the synchronization from the access point. Now we turn on the last tag. In this case, instead of using NFC, we can use a push button. We use push button 2, and this will start again advertising. Now it's connected. It receives an image and it gets disconnected. So now it's synchronized as well. All of them are synchronized. They belong to the same group number 0. In this case, we have for this tag we have a ESL ID 2. Now we want to trigger some action because all of these are synchronized, these tags, and to trigger the action we send some commands. Now we can use the shell command to send commands as we have done, as we have seen previously, but in this case, again, for the simple out-of-the-box experience, we have pre-programmed some behavior in the bottom 3 and 4 of the access point. So we can send some predefined commands. This is explained on the tutorial, how this behaves, but for example, we can press button 3 and this will trigger a new image on all of these devices. This does not have a display, so you can't see, but it will there is an LED that signal having received a command to change the image. You can see also that in the PAwR profiler we have gone through this this procedure. So the tag was synchronized, it received the packet, it changed the display image, and then goes back automatically to sleep in synchronized state. We can do again, and we can press the same button, and we will see that as soon as I press the button, we send another command to these tags to change the image to display the first the image number 1 instead of 0, and you can see that the images have been changed quite quickly. And we can see that here also on our screen, on our shell commands, we can see that we have sent a message on to the group 0, and we have sent another message to the group 0 again, and the first was to display image 0, now it was to display image 1. We can do in a similar way, we can turn on and off the LED lights. So by pushing button 4 we can we can ask the tags to start blinking the LED, and you can see this is both here and here as well. It's not visualized on the on the first development kit, because here we have a power measurement going on. This is the message that we send is to blink for a number of seconds, but we can try it again to blink, and then by pushing it again we can stop this blinking. You can see it here on the PAwR profiler. You can see that the message has been received to turn on LED. This is processed, and this is the LED pulses. And then when we send again another message to stop this LED, and we go back to sleep. This is basically the out-of-the-box demo. Then, as I mentioned earlier, we can still use the shell command to send some specific command to some tags. And in this case, again, we asked we send a message to turn on the LED to all the tags in group 0, and this is happening here and here. Here again we have the current measurement going on, so we don't see it, and we can we can change the image using another command. And here we got the responses back from the 3 tags. So this is the out-of-the-box demo that basically with a few steps using precompiled hex files you can demonstrate the Bluetooth ESL functionality, and then you can learn more about more advanced topics on the access point, on the tags, by reading the Bluetooth ESL tutorial by Nordic. This concludes the presentation. The best way to get started is to go to the Nordic website at nordicsemi.com/ESL and download the Nordic Bluetooth ESL Getting Started Kit, which includes the Nordic Bluetooth ESL tutorial. You can start easily by following the tutorial, even if you don't have displays with you, just with a couple of dev kits as mentioned in the tutorial under the hardware requirements section. If technical questions, you can always contact directly the Nordic engineers at the Nordic Dev Zone by opening a public or private ticket, or you can contact the Nordic sales by following the link below. Hope this training has been informative, and thanks for watching.